thanks everybody for inviting me along. I think Nick gave a pretty good introduction sort of to my space of interests, and I'll tell you a little bit more about them in the coming 20 minutes. In terms of mixing, I should mention very briefly that I will be swapping panel sessions with my colleague Sofia Ojeda, who's in the front here. So if you have really any hard questions for me, save them for Sofia, and I will appear in the signal processing panel later this afternoon. So we'll mix it up a little bit from the very beginning. So the title of this talk is Big Data and Imaging, Challenges and Opportunities. And there are really three things I want to do. Since this is more of an overview talk than a technical talk, I basically want to walk you through a sort of very short, recent history of imaging from a mathematics perspective and kind of tell you first how we got to where we are today. Then I'll spend a little bit of time talking about some of the key drivers of today's challenges in big data as it applies to imaging. So I'll talk a little bit about dimensionality reduction and about different notions of dimension, intrinsic versus extrinsic. And the final thing I'll do is just point out some areas that you may want to pay a little bit of attention to, because I think it's possible or even likely that they'll come to the fore in the coming years and maybe even the coming decades. So that's really how I've structured the talk. It's only a few slides, and I'm really going to talk to some of the pictures. So let me start by telling you a little bit about how we got to where we are today in terms of imaging. And I should say that I kind of came up, my own background is in statistical signal processing and imaging, and I sort of came up around the time that the multi-scale revolution was really happening in imaging. So if you turn back to the 1970s and the 1980s, things like the fast Fourier transform existed, and communities were starting to understand how to take large quantities of digital data and think about doing something with them. At the same time, it became apparent that the sort of mathematical origins of imaging were about understanding what does the mathematical space of naturally occurring images look like. How does one compress an image sampled at random from the space of all possible natural images? How does one think about removing the noise from an image or acquiring an image in a good way under, for example, low light conditions or in microscopy, any of the equivalents to low intensity conditions? So all of these things kind of came together to kind of build the mathematical origins of imaging. And some of the biggest things that happened in the 1990s, I've listed on the slide here. So first of all, it came to be understood that there were many different approaches one could take to smoothing. Smoothing an image can be viewed as just blurring it out. Our eyes essentially do this. We apply a kind of a low-pass filter to the images that we see. Sometimes a sampling or acquisition mechanism will apply a low-pass filter to an image, even if that's not what we wanted. And it turns out that purposefully smoothing an image can even be a way to understand it. So computer vision specialists will talk about scale space and imaging. So if you take an image through a various sequence of smoothings, you can watch which features persist at different scales across the image. And that can lead to some interesting understandings of image structure. So the last thing that's mentioned here on the left is the idea of multi-resolution. And that's illustrated by the pictures I've put on this slide. So this really came about through methods like wavelets and splines. And the basic idea here was to understand that this intrinsic multi-resolution or multi-scale structure of images could be leveraged to yield fast transforms. So if you have n data points, the fast Fourier transform takes order n log n operations. There's a fast wavelet transform that takes order n operations. So suddenly you had a coming together of a mathematical understanding of image structure along with fast algorithms that allowed the analysis tools to be applied to larger and larger data sets. Now, we weren't really in a sort of big data era in the 90s, but we could already begin to see that technology was going to generate larger and larger data sets, especially in the areas of medical imaging, because of the rate at which technology was increasing. right? So I've talked a little bit about noise and variability. So I've worked on several problems in this area in my career, mostly with Sony and with Texas Instruments. So I'm talking about visual wavelength imaging. And the biggest changes that I saw from, say, the early 2000s until now have really been that when I started, we were very focused on sort of fundamental primitive signal processing problems. So an ex-Polaroid executive told me that his favorite trick when they came to him with a new camera was to stick it under the desk in the conference room and see how bad the picture was in low light conditions, right? So we spent all kinds of time trying to deal with the Poisson nature of data in low light conditions. And astronomical imaging still has exactly this feature, all the way down to things like single photon detection, right? But what's happened is that instead of, sensor design has begun to take care of those problems. And instead what we see now are things that are at a much higher level of abstraction coming into the imaging process. So things that would have seemed like magic 30 years ago to computer vision experts are now on your iPhone camera, right? Face recognition, smile detection, all of these kind of very, very high-level features that are sort of a world away from simple questions of noise and variability are now basically implemented in commodity hardware that in some sense has no margin, right? So it's one of the reasons I got out of this area, actually, was I mean, not for the margin reason, but it's very difficult to get. We patented lots of technology, but it's very difficult to convince companies to pick up when all you have to do is wait another year and the sensors continue to get better and better, right? Hardware keeps getting better. Anyway, so there are some fundamental limits. I mean, the larger the charge coupled device, right? The larger the flux of a photon arrival, the better imaging potential we have. But even I looked recently at the latest Samsung camera on a phone, and again, the cameras are starting to get even a little bit larger. I don't just mean number of megapixels, but the actual physical size of the camera and how much light it's letting in. So anyway, so that's a little bit of a history of how we got to where we are, at least from my perspective. And I think, again, the main thing that's interesting here is the sort of mathematical tools that have been fundamental to this kind of progress. Every time you download a JPEG file, you're using a multi-resolution compression scheme, and it turns out to be very efficient and effective. So next, I wanted to talk about some of the things that are driving our imaging challenges today. And the main one, the most important one, I'd like you to think about is the idea of dimensionality reduction. Okay? So what does that mean? Well, in 1901, Carl Pearson, who was actually the founder of my department, came up with this idea that we now know today as principal components analysis. And his basic idea was that if you have a point cloud and you can determine the directions of greatest variability in that point cloud, and you can project the data in those directions, thereby reducing its dimension. Okay, that's the basic idea of dimensionality reduction. About 50 years later, several people improved upon this idea, one of whom was Tucker, with the idea of a nonlinear type of dimensionality reduction. And that's actually what's shown in the picture here to the right. So what you've got on top is something that looks like a fishbowl. It's basically a whole bunch of points that have been randomly generated on the surface of a sphere, except I've taken the top cap off the sphere. I've cut it as if it were a fishbowl instead of a sphere, right? So you ask yourself, what is the dimension of that object? I think it's on the order of a few thousand points here just for visual purposes, but you could imagine it being millions of points distributed on the surface of a sphere. Is the dimension of this object fundamentally 1,000,000, or is its dimension 3, or even perhaps is its dimension 2? Right? So if you use Pearson's technique from 1901, and you unfold this fishbowl into a disk, things don't go so well for you, because looking at the directions of greatest linear variability in this object doesn't help very much, right? This isn't really a point cloud. It has a more fundamental or complicated low-dimensional structure. It's a two-dimensional object that's embedded in three-dimensional space, right? But even going back to the 50s, plenty of things like multidimensional scaling will successfully sort of unwrap or unfold this object. And I've given a couple examples that are labeled C and D here. It's not really important what these methods are, but the main point is that you can see that the red sampled points, which are around the boundary of the fishbowl, get unwrapped to the outside, and the dark blue points remain in the middle. Okay? So there's lots of ways to think about this. These were actually done using random projection methods, which turn out to be more efficient sometimes in terms of space and time. And that leads on to into an idea called compressed sensing that I'm not going to talk about here, but that you should be aware of and that we'll revisit in a few minutes. So the main idea really is that somehow, given an object of potentially very large dimension, I need to understand, or we need to understand, the true sort of intrinsic dimensionality of that object. Whether you took a selfie on a Polaroid camera or whether you've taken it on your latest many megapixel iPhone camera, affects the extrinsic dimensionality of the object, right? It affects the number of pixels, the number of sampled points. But it may or may not have anything to do with the true underlying intrinsic dimensionality of the object. And so we have many ways to study that and understand it mathematically, most of which boil down to something about the power of projections. Purely linear projections were the technique that Pearson discovered in 1901, and that's principal components. And we all use PCA probably almost every day of our working lives if we work in imaging, but yet it's not the whole story. PCA won't work on this fishbowl example, but plenty of other unwrapping or unfolding methods will. So that's something that's worth thinking about. It's often about a search to understand the underlying intrinsic dimension of the object that we're sampling or acquiring or otherwise studying. And mathematics is very good at coming up with new and powerful techniques for realizing these type of projections. And that's, in some sense, the sort of hunt for dimensionality reduction in the context of imaging. So to continue with that point, I thought I'd give an even starker example of this. This example comes from computer vision, but it could just as easily apply to a population of clinical images, for example, of perhaps malignant and benign tumors, for example. So what have we actually got here? We've got an even starker example of the difference between intrinsic and extrinsic dimensionality. Each photograph here, each picture, each image is a few megapixels from the time when this database was put together. It's a computer vision database. And what you can see looking around is that the person who's being videoed in this, these are stills from a video, is slowly moving his face. He's adjusting the orientation in 3 space of his head, right? So ask yourself again, what is the extrinsic dimensionality of any one of these stills, or what is the extrinsic dimensionality of the video, right? This is the problem you face when you're at the Heathrow and you want to download something to watch, using iTunes on your flight, and there's not enough bandwidth on the local network, right? That's about extrinsic dimensionality. But it turns out, if you look carefully, that there's so much natural physical structure in these images that they can be reduced to a curve in 3-dimensional space. A parametric curve such that as you move along this curve from start to finish, this curve, which is wrapped up and embedded in 3-dimensional space, actually follows very smooth orientation movements of the head of the person in this video example, right? So there are all kinds of interesting questions here. There's a question of whether you do this kind of processing in batch or in real time. And there's the question of whether you have to hold on to all of the data in order to do it. So that leads to areas like sketching, streaming, and subsampling. In other words, if you think of the fire hose model for big data, a giant video stream that's just kind of like whooshing by at every instant, how much do you need, you sort of dip in your ladle and take a little bit of data out. How much do you need to do in order to achieve this type of dimension reduction? So this is a very, very active area of research. So that's kind of where we are today. all of these things are problems that I've worked on, and they're from sort of the past few years. I'm not saying that any one of them is state-of-the-art for any particular application, but they give you a sense of the general thrust. So let me just finish with a few words about horizon scanning and about what we might want to think about next in this context. So when I look forward, sort of in the 3 to 5 to 10 year time frame, and this is certainly something that I'm going to push my colleagues at the new Alan Turing Institute to do, when I look forward, what I see is that different branches of mathematics in this general space are starting to come together. So applied mathematicians who use tools like partial differential equations to understand image smoothing are starting to talk more and more with statisticians who, like myself, use an entirely different set of tools based on probability theory to look at image smoothing, right? So different branches of mathematics are coming together. Our understanding of inverse problems has advanced quite a bit. So in general, all of the things I showed you about dimensionality reduction are a kind of an inverse problem. We have a vague sense that there's an intrinsically low-dimensional object of interest, like the line rolled up in 3-space that I showed you in the last example. And our inverse problem is to recover this low-dimensional structure from the things that we observe in potentially a very, very high extrinsic dimension. That's, in some sense, the essence of the big data problem. I talked a little bit about compressed sensing. Compressed sensing is a way to use the idea of random projections almost in reverse. So instead of projecting a high-dimensional object down to lower dimension to understand it, we skip that step and we simply acquire the object through a sequence of random projections. And under certain conditions, it'll be possible to recover the underlying base object. So that tells us something very interesting from a dual perspective about this problem of dimensionality reduction. And compressed sensing is, it's not necessarily the way that an engineer would design a system to perform any particular imaging task, but it has the power of providing a framework for understanding that kind of works in a variety of different settings. So it's really, I think, a tool for understanding the mathematical structure of imaging scenarios. So the last things I'll say are just the other thing that we see is as technology continues to give us new imaging modalities and as scientists across disciplines talk to each other more and more, there's more of an interest than ever in kind of merging models. So fusing image data or acquisition data from many different sources, taking imaging modalities that measure at different scales, and also kind of looking to combine different multimodal types of imaging and other data. So I think that's going to be a big challenge for us in the coming several years. And the last thing I'll mention, I don't know how many people have heard much about this, but there's a lot of excitement in the machine learning community about some sort of artificial intelligence techniques, I'd almost call them, that go under the heading of deep learning. So these are basically sophisticated dimensionality reduction methods that don't right now admit any kind of open understanding of precisely what is happening. So I can tell you a story about how the dimensionality reduction works in each of the examples I showed you. I can write down equations. I can show you exactly what's happening. Deep learning is what turns out right now to be, in certain circumstances, a very effective but at the same time currently opaque method of understanding a potentially much more powerful form of dimensionality reduction. So I've listed it with a question mark here because I don't think any of us quite knows where this is going to go. But in applications where we're willing to trade off understanding against performance, things like deep learning may have a powerful impact. In other areas like imaging for clinical understanding, I think we'll probably end up staying within the space of mathematical techniques that are more understandable. So I think I'll leave it there since we're just about out of time. And I will say I think we'll defer questions for later. Thank you very much.